So is that stuck in your head now?
It's just
All right, so we'll talk exam. Do you want to do exam at the beginning or at the end? What do you think we're going to do? We're going to do end, so.
he's smart.
I'm not that.
Measure their heads.
So there's homework due tonight, and I'm just going to go ahead and tell you we're not going to get done with it. So I was thinking about what to do. So one option was to move the homework due to Friday, but I'm a little bit of a realist and recognize that people aren't probably going to be all about doing homework on Friday. So then I thought of moving it back maybe over even to the weekend, and I thought, well, I don't even know if I'm allowed to do that. That's reading. So here's what I decided we're going to do, because there are really useful homework problems that you will be able to do as of Friday, and will be important on the exam, but it's on today's homework. I'm just going to pull those off, and so right after we get out of class, I'll see how far we get. I'll yank the problems that you aren't going to be able to do off of the homework set, and so the stuff that you can do will be due tonight, and the other stuff we're just going to kick down the road. And so I always make a practice version of the sapling available, right? And so I will just open that up so that you'll have access to the other questions before the final exam, so you'll have a chance to work on those, but they're not going to end up counting for a grade. So I thought that was probably the best solution. So we're going to have a workshop today. I think we'll go something like 4 to 5:30 or so. People with Wednesday afternoon labs should be done by then. And then I'll get out an office hour schedule for the rest of this week, and then early next week. I've just been I've been busy, and so I'm a little less busy now, so I can actually get that schedule out. In terms of evals, I just looked.
Are we more awesome than 11 a.m.?
I don't know.
Yes, you do.
I mean, I do. You're about to know. So 10 a.m., the response rate is 59.48%, which is very precise, right?
I know.
Considering there's like 150 people total. 11 a.m.
Is it 60? Please tell me it's 60. Oh, no, wait, we're 10 a.m. No.
What happened?
You know what's sad? That's like
that means that there's still 40% of the class that even though I gave you, my gift to you on Monday was that of time. I gave you 5 to 10 minutes. All I asked was like 2 of those back.
Well, Dr. Walk, who has the bigger class?
Well, I mean, so they're actually identical, or they're like one off. So they're very similar in size.
So they're like a 5%. It's like a 5%.
Yeah, it's roughly a, you do the math. It's that amount difference. Yeah, go ahead.
When do these close?
These close on Friday night.
Okay.
I had some colleagues tell me I should not have left them open until Friday night.
But that's when you get the brutal honesty.
Yeah, that's the brutal honesty right there. All right, so yeah, that's that. Any questions about stuff? Man, we're getting so close. 2 classes now. My throat hurts. Don't make me yell. Let's quiet down. Okay. So our theme song today was "All Together Now" by the Beatles, which you've now heard about 6 times. And so we're going to go Roman numeral 4. We're going to say, let's tie it all together. See what I did there? All right, so let's tie it all together now. How do we do this SN1, SN2, E1, E2 stuff? All right, so I think the easiest way is to do some sort of flow chart. And so first, the simple flow chart. So the simple flow chart is going to ask, can you do SN2 or E2? So you ask yourself that question. So if the answer to that is yes, then do it. Do one of those two things. Don't ever try to be looking to do SN1 or E1. You want to see if you can do SN2 or E2. That's the first question that you might ask yourself. And then, of course, if the answer is no, well, you're not going to do SN2 or you're not going to do E2, then you've got to consider the possibility of doing SN1 or E1. And remember, we're not going to ever tell any difference between SN1 or E1. They go mechanistically, do the same rate determining step first. We're going to form a carbocation. We always see both things happen together. All right, so that's going to be a pretty complex mixture whenever we go through a unimolecular process, giving us SN1 or E1. Okay, so let's see. We're going to make now a more complex flowchart. And so really the flowchart that we're going to make, it's going to center around the question, what kind of Rx do we have? What kind of alkyl halide? Because the thinking is different depending on what kind of alkyl halide we have. So this is all centered around what kind of Rx do we have? And so we're going to go through the four possibilities and make a flow chart for each. And we're going to see that it's not really all that complicated once we have it down on paper. Yeah, Josh?
What does RX stand for?
That's your alkyl halide.
Okay. Because I keep reading his prescription.
It is not that. Okay, so our Rx is our alkyl halide. And so let's see, we're going to start with our methyl alkyl halide. And so we saw that our methyl alkyl halide was already relatively simple because we can't do elimination, right? There's no beta hydrogen, and so we don't even have to consider elimination pathways. So what we're going to ask ourselves anytime that we see a methyl alkyl halide is we're going to think to ourselves, all right, do we have a strong nucleophile? That's what we want to ask. Do we have a strong nucleophile? And so if we do have a strong nucleophile and our answer to that question is yes, what kind of mechanism are we going to follow? Yeah, SN2 in this case. So if the answer is yes, we have a strong nucleophile with a methyl alkyl halide, we'll do SN2. If the answer to that question is no, what are we going to do? Can't do elimination, can't do SN2, can't do SN1 because how stable is a methyl carbocation? It's not very stable, and so nothing's going to happen. That's pretty much it. That's it for a methyl alkyl halide. If we have a good nucleophile, we'll go SN2. If we don't, we'll have clearly a frowny face of some kind. Alright, so nothing will happen, and I'm not going to be tricking you on any exam. I'm not going to give you something where you have to decide if it will even react or not. So you're always going to have a product from a reaction of some kind. I'm never going to lead you down the other road. Okay, so that's a methyl, and that's pretty straightforward. So next we'll look at primary alkyl halides. And so we'll ask ourselves again the same question. That's pretty convenient. Strong nucleophile? We ask ourselves. All right, and so if the answer to that question is yes, what kind of mechanism will we do? SN2. All right, we're seeing some similarities there between the methyl alkyl halide and the primary alkyl halide. So if we have a strong nucleophile, we're just going to roll forward with SN2. Okay. Now there's certain cases where we'll say, no, we don't have a strong nucleophile, all right? So for example, something like potassium tert butoxide, we don't consider a strong nucleophile. And so we have to think about another property of that potassium tert butoxide. And in particular, we're going to ask ourselves, is it a BBB? What is that?
Big bulky.
That's a big bulky base. We have to ask ourselves, is it going to be a big bulky base? Okay, so if the answer to that question is yes, what will our mechanism be? That is E2. That is our special base that we're basically going to use as a strategy to promote elimination pathways. And so in that case, we're going to roll forward with an E2 reaction. And so if it's not, that means that we don't have a strong nucleophile and we don't have a big bulky base. And so what if the answer to that question is no? It's just sadness. That's it. And so again, so methyl's not that hard. Methyl, we go SN2 or we don't do anything. Primary, we go SN2 with a strong nucleophile, unless we have a big bulky base, and then that. Gabby?
This is a bad question, but why is that a not strong nucleophile?
So it's not a strong nucleophile because it's too bulky, basically, right? So certainly we expect a negatively charged oxygen to be a strong nucleophile, but because it's connected to that big bulky group, and remember, the property of nucleophilicity is we measure rate, right? It's based on how fast does it act as a nucleophile. So we can throw that in there with a primary alkyl halide and try to measure its nucleophilicity, but we're not going to see any SN2 reaction take place. And so we can pretty much say it's a bad nucleophile. Even though it's a negatively charged oxygen, the rate of reaction is pretty much zero because of that congested transition state, and so we say it is a bad nucleophile. Yeah.
What if you have a base that is strong but not big and bulky?
A base that is strong, but it doesn't matter. And so if you go back in your notes and you look at the primary section, basically, because the primary alkyl halide is so unhindered, if it can act as a nucleophile, it's going to do that and go SN2.
So if you have a base that's a really strong base but it's not bulky, you'll do SN2.
If you have a strong base, say that again.
Like if it's a really strong base but it's not big.
If it's a really strong base, anytime we're going to have a strong base, we're going to have a negative charge on some heteroatom, like an oxygen or a nitrogen. And in that case, that's going to act as a nucleophile with the primary alkyl halide. Basically, if we can do SN2, if we have something that can act as a nucleophile with the primary alkyl halide, we're going to do SN2. And it's just because the transition state is so uncrowded.
So that crowded base only refers to a weak base.
Yes. Well, yes. Go ahead.
How do we tell that something is a big bulky base?
So we learned in terms of big bulky bases, we learned terbutoxide, and honestly, that's what we'll use. So pretty much the only big bulky base that we'll see is going to be that terbutoxide. There are other ones, but this is pretty much that's the one everyone uses. I've used this a ton in my career. Okay, so then we move on to secondary. So secondary is the most complicated case where we have to think about a few extra things going on. So let's, I'm gonna actually go down.
Does the brownie base mean no reaction?
Yeah, maybe I should clarify. No reaction. I get a little too cute sometimes. I should maybe actually clarify what I'm trying to tell you. All right, so frowny face means no reaction. Just in general in life, if you ever see a frowny face, no reaction. All right, so next we'll do secondary. Okay, and so with secondary, just for, let's see, how do I want to, I have this in my notes one way, and I thought about doing it another. And so what I want to do is I'm going to start with the question, we're going to change it a little bit. We're going to ask, do we have a strong base? Right, because the way we tell the difference between SN2E2 is based on the conjugate of the base or nucleophile in question, so we look for that pKa of 11. And so if it is a strong base, and the answer to this question is yes, what kind of reaction will we do? We will do E2. And so remember, when we say yes to that question, we're saying that the conjugate has a pKa that is greater than or less than 11. Greater than 11. All right, so, of course, let's see. If we say no, we're then going to ask ourselves the question, do we have a strong nucleophile? All right, so, in this case, if we don't have a strong base, but we do have a strong nucleophile, what kind of reaction are we going to do? That is going to go SN2. Let me make sure I'm happy with this thus far. Okay, so if we don't have a strong base and we don't have a strong nucleophile, what do we think of then?
SN1E1.
Then we want to think about unimolecular pathways. Now we can make a stable carbocation, and so we can go SN1 or E1. All right, and I'm kind of doing this on the fly. Let's make sure this makes sense. So basically, we look if we have a strong nucleophile or a strong base, and so if that is a strong base, we're always going to do E2, so that's what our flowchart says that we're doing. If we don't have a strong base, that means the pKa of the conjugate is less than 11, and so then we ask ourselves, is that a strong nucleophile? If it is, we do SN2. If it's not, then we're only left to do SN1, E1 processes. Everybody happy with that? I think that's it. All right, so that is our case for the secondary alkyl halide.
We're not differentiating between SN1. We're not going to be asked to decide whether to do SN1, right?
No, anytime you see SN1, E1, you're going to get both products. They're both going to happen. So then finally, we get to our tertiary case. And so again, our question is going to be, do we have a strong base? And so if we do have a strong base, what mechanism will we do?
E2.
E2. If we don't have a strong base, what's up?
Strong nucleophile.
Well, can we ever do a substitution reaction at a tertiary position? An SN2, I should say. No, we can't. And so if we don't have a strong base, the only other pathway we can do is to create a carbocation, which is going to lead to what products? SN1 and E1. And that's pretty much it. That's it all tied together now. So, all right, so I think the easiest way to do, and we'll go back and we'll just kind of look back through this. So the easiest thing to do is think to yourself, well, first off, what kind of alkyl halide do you have? Because that's going to be the big question that's going to impact the way that you're thinking about this. And so then you're just going to go through these little flow charts, and you can see, honestly, it's relatively straightforward for each. So questions about that? We're going to do a bunch of examples. Okay, let's do a bunch of examples. Oh yeah, first off, so I did a little back of the napkin calculation yesterday. And so this is what Meldrum and I were doing. So we figured out that in Orgo 1, and I'm not proud of this, I'm going to try to decrease this in the future. We are going to have used 10,800 sheets of paper this semester, which is insane. That's so much paper. And so we looked it up. And so that equals, I forget exactly, it's equal to something like 1.3 trees. So we've used over a tree of paper in organic chemistry. And so in honor of Earth Month or Day, I'm going to try to decrease that in the future. Actually, Meldrum had that idea. He was like, you guys should go outside and plant a tree. And then, so that I can then cut it down and have paper for next semester. Yeah. Okay, so I was pretty amazed by that. I've also been lugging around that much paper, like to my house and things. All right, so let's do a bazillion examples of this. All right, so let's see.
So when we're looking at the secondary alkyl halides,
Yeah.
how can we because nucleophilicity and basicity are related, right? So if it's not a strong base, how can it also be a strong nucleophile later on?
Yeah, and so what it is basically we're gonna have cases with SN2, or I'm sorry, with secondary alkyl halides where we have something that is both a strong base and a strong nucleophile, and it's just that the basicity wins out. And so that's why we ask ourselves the question first: is it a strong base? Meaning it doesn't have that conjugate greater than 11. If the answer to that question is yes, then that's it. That's all we care about. We care about that basic property. If it's not, then we ask ourselves, well, it may not be a strong base, but is it still a good nucleophile? So something like chlorine, right? It's not a strong base, but it's a great nucleophile. And in that case, we can go SN2. Yeah. Rhea?
So do we not have to worry about the strong base question for the methyl and the primary?
What's that?
We don't have to worry about like if it's a strong base for the primary, or we don't start with that question.
So you definitely don't have to worry about the strong base with the methyl because you can't do elimination anyway. And so with the primary, what it is that even if you've got a strong base, and that's where the big switch is with a primary alkyl halide, you can have something that's both a strong base and a strong nucleophile, but because that transition state for the SN2 reaction is so unhindered, the nucleophilicity wins out. Okay. And so pretty much that's one of the big key differences between the primary and the secondary is that with the primary, nucleophilicity wins. With the secondary, basis wins. Okay. And so yeah, I put these together because I think this is the easiest, most straightforward way to get right to whatever kind of reaction you'll be doing. Okay, so we'll take this bromide and we'll treat it with sodium methoxide. And so let's think, what kind of alkyl halide do we have?
Primary.
Definitely a primary. Now let's ask ourselves right here, what kind of nucleophile is sodium methoxide? We have a strong nucleophile. What kind of base is sodium methoxide? It's a strong base because its conjugate is methanol, right, with a pKa of about 16 or 17. And so we can go back up to our flow chart and we can actually see, well, the basicity doesn't even matter, right, unless it's a big bulky base. Is this a big bulky base? No. This is not a big bulky base, but it is a good nucleophile, and so that means we're going to do what reaction? SN2, and so we end up with this product, SN2. Josh?
Well, wouldn't the fact that whether it be a big bulky base or not matter because it's a strong nucleophile? So
Well, I guess the difference is we're never going to have big bulky bases that are strong nucleophiles. They're not strong nucleophiles because they're so bulky. They can't actually act as nucleophiles. Okay, so that's pretty straightforward. So the next one, we'll go with this alkyl halide. So what kind of alkyl halide is it? Secondary. So now we've got a secondary. We've got the same thing here. We've got a strong nucleophile. We've got a strong base. But our thinking is a little different now. And so the first thing we ask ourselves, it's no longer about the nucleophilicity. We ask, is this a strong base? And so we know that it is, right? Because its conjugate is a pKa of around 17. And so if it is a strong base, what kind of reaction do we do? We do E2. And so we get the elimination product just like that. So here is a perfect example of that difference in thinking between primary and secondary. For primaries, we're just looking for nucleophilicity, basically. For secondaries, we now have to draw that line and consider, does the basicity win or does the nucleophilicity win?
And the base wins here because it's secondary?
The base wins here because it's secondary and also because its conjugate has a pKa of 17, which qualifies it for a strong base. Yeah?
Can we have the double bond on the other?
You could, it'd be the same exact
All right,
product.
sweet.
Yeah.
But that pKa doesn't matter for the primary.
Correct. Yeah.
For example, we had this on the final. We have to draw resonance because it's double bond.
So there wouldn't be any resonance in this one, right? Because this is an sp3 carbon right here. So there wouldn't be the only way we'd have resonance is if you had a structure, if you had like the cation here, right? And then you would have resonance, or you could also have the anion there, which could undergo resonance.
That you could draw it where the double bond would go.
You could draw, you could draw that product and it would be the same exact thing. It's the same molecule, it's just flipped over.
Okay.
Yeah. And remember, if you're ever questioning if it's the same molecule or not, give it a name. And if the name is the same exact thing, then you know you have the same exact molecule. Okay, so let's use that same exact secondary alkyl halide. And so now we're just going to hit it with methanol. All right, so we're still secondary. What kind of nucleophile? It's definitely a weak nucleophile. It's a neutral oxygen. And so it's also a pretty weak base, right? Because what's the conjugate of methanol? The conjugate acid of methanol. Remember, it's going to be protonated methanol, like that. And so we would assume that has a pKa of around -2 or so, kind of like hydronium. And so we know that the methanol would be a weak base. Okay, so we think we don't have a strong base, so we're not going to do E2. We don't have a strong nucleophile, so we can't do SN2. And so what are we left to think about? Yeah, we've got to go carbocation. And anytime we go carbocation, we're going to have to do both possibilities. So we're going to have our E1 product, which looks similar to our E2 product. And we're also going to have our SN1 product, which I guess looks similar to our SN2 product. Like that, not OH, O-methyl. All right, so here's our E1, and then here is our SN1. And so on the exam, you're always, if I ask you for the products of this reaction, you need to draw both the E1 and the SN1 products. Yeah.
Why did the hydrogen break off in the
Yep, and so what it is you're gonna, once you have your carbocation, you're gonna go through a mechanism where we've got cation plus methoxide. And so you will add that in there. To end up with this.
Oh, and then
Yeah, but then we'll deprotonate because we always want to have a neutral final products, and so we'll use a base of some kind to deprotonate to get us to our final product. Yep. All right, next up is this alkyl halide with sodium methoxide. All right, what kind of alkyl halide? Tertiary, that's pretty crowded. And then do we have a strong nucleophile? Yeah, do we have a strong base? Yep. Okay, so with a tertiary alkyl halide, what's the question we ask ourselves? Yeah, we first ask ourselves strong base. We do have a strong base, and so what kind of reaction are we going to do? E2. We're going to do E2. So we end up with this product right here. And so this is one of those cases where even if this wasn't a strong base and it was a good nucleophile, would we ever be able to do SN2? You never do SN2 at a tertiary center anyway. So in this case, it's either E2 or it's carbocations.
Is that product the same no matter where you put the double bond?
Yes. Yeah, because you could also have, say, this product, but again, that's just rotated, right? So. So then we've got the same alkyl halide, so we've got a tertiary. And this time we'll just stir it in methanol. Alright, so it's tertiary, and so we ask ourselves, do we have a strong base?
No.
We don't, and so what are we going to do? Yeah, we're going to have to go a carbocation pathway, and if we're going a carbocation pathway, what products do we get? Yeah, we'll get SN1 and E1. So our E1 would look just like the E2 above. So here's our E1. And then our SN1, we would substitute a methoxy group in. And again, we're gonna lose that hydrogen in a deprotonation process. All right. So now let's go to this iodide. So what kind of alkyl halide? It is a secondary. And so our reactant is going to be sodium acetate, which looks like this. And so what that means is that we've got a negatively charged oxygen there with a positively charged sodium there. Okay, so with a secondary, we ask ourselves what first? Do we have a strong base? Is acetate a strong base? It's a negatively charged oxygen. But let's think about that for a sec. So acetate looks like this, and so the conjugate of acetate will be this molecule. So what is that molecule? It's acetic acid. And so acetic acid is an alcohol, of course. It's a carboxylic acid with a pKa. Where would you estimate a carboxylic acid pKa? 4-ish, maybe, somewhere around there. And so if the pKa of acetic acid is around 4, does that qualify acetate to be a strong base? No. It is not a strong base. And so it's not a strong base, so we go to our next question, which is, we ask what kind of nucleophile it is. And so it's a negatively charged oxygen. What is that? That's a strong nucleophile. And so since that's a strong nucleophile, what kind of reaction do we do? SN2. So we would end up with that right there. So if you have trouble seeing that, just count 1, 2. Ah, go away. I can't. My little red mark won't go away. There we go. So we'd say 1, 2, 3, 4, and so here we count 1, 2, 3, 4. And so you can see that you're connecting that oxygen number 3 just to that alpha carbon of the alkyl halide, as we've been doing. All right. So there's some really, and I highly suggest you take a look at the extra homework problems towards the end of what I posted yesterday. They're really good, and so those are going to be sort of like this. And so we're going to start thinking about not just what product will we get, but we want to ask ourselves, how can we get to a product given a certain reactant? And so let's say you're given this starting material and you're given this product. So you're asked, what can we put there to basically make this transformation go? And so of course I would always think, well, let's see, we've got a primary alkyl halide there. So what kind of mechanism are we going to try to do with our primary alkyl halide to go from starting material to product? E2. So we could think about doing E2. And so what kind of reagent would we have to treat it with to do E2? Not just a strong base, remember, because we don't, when it comes to a primary alkyl halide, we're mainly concerned with nucleophilicity. What special kind of strong base will allow us to do an E2 in a primary? A bulky base. And so in this case, we've got to make sure that we use a big bulky base. And so I would just use something like potassium terpbutoxide. You can use sodium terpbutoxide. Those are probably the two most common. Honestly, if you just put terpbutoxide, I'd probably be happy with that. Okay, so another example of that. Let's say we've got the same starting material. And really, I think this is a really, really good exam review right here. So, let's say we have that product. And so this takes maybe a little bit of thinking.
Well, it requires a shift.
Yeah, we have to have a shift of some kind, right? And so we know that we can get a shift through some carbocation pathways. And so if we think maybe going SN1 or E1, however, I think if you draw that out, you're probably going to see that that's not something that works. So another thing we could do is, again, what we could do is we could think about making this product and then seeing if we could come up with some way to get from this product to this product. So let's see what we can do. So number one, I'm going to say first, let's hit it with our big bulky base. And so if we hit it with our terpbutoxide, we're going to end up with this product. And so now we've got to think about how we can go from that to that. Any ideas? And so this is why this is good review, because this isn't from this chapter. How can we go from this alkene to this product? It's a Markovnikov addition, right? And so we're doing the Markovnikov addition to form an alcohol. And so what's one way we can do a Markovnikov alcohol addition? How about water with catalytic acid, right? And so if we do water with catalytic acid, we know we're going to end up doing the Markovnikov process, right? So here's what this will look like. We'll protonate here. And so when we protonate, we're going to end up with this carbocation, right? And so we've got that carbocation in solution with water. And so we should be able to see from there how now our water can attack the carbocation. And after a deprotonation step, we would lead right back to that. Yeah. And so there's a bunch of good homework questions that are going to require you to think about how you can do multiple steps to get from a starting material to a product. This is, so this is maybe the first time you've seen sort of the multi-steps. This is kind of what I think is awesome about this, is this really is devising like strategies to get from one end to the other. And so the homework questions, there are a few that even ask you for 3 or 4 different reactions to go from one end to the other. So just take a look at those. It should be really good practice. Okay, What time is it? It's 10:35. Are we even going to touch alkynes? Let's do a little bit of alkynes. All right, so chapter 7. You guys got really quiet when I did that example. That's part of the challenge of organic chemistry is using, basically, the goal of this is we provide you with a toolbox over 2 semesters of lots of different chemical transformations, and then you're able to use those tools in your toolbox to go from one thing to the other.
Is that more what Orgo 2 is like, or is it like, is there...
I'd say like in an Orgo 2 exam, I would expect more questions like that, where you're expected to kind of put the whole puzzle together. On our exam, we might just have a little piece of that.
Yeah.
All right, so chapter 7, alkynes. So we're just going to do a really whirlwind intro because alkynes are pretty boring. So Roman numeral number 1, I hope there are no alkyne lovers in there. So a really common alkyne is this one, and so this gets the special name acetylene. So like an acetylene torch is using basically ethine. So the IUPAC name here would be ethine, but literally no one says ethine, so don't do that. And so let's think. In an alkyne, we have sp hybridized carbon, and so that's going to give us linear geometry. So that's why we're always drawing our alkynes with the linear geometry. We've got our sp hybridization, so those electron clouds are going to get as far apart as possible. So in terms of naming, we treat it very similar to an alkene. And so our example for naming, and don't let this throw you off, this is how it's drawn. And so how many carbons are in the longest chain here?
8.
Yeah, it's 8. And so the way this is done, and again, I didn't create it, it's just how it's done. We always say that a terminus or an angle is a carbon, except when there's an alkyne involved, and then the position where the single switches to the triple, that's also a carbon. So we've got an sp hybridized carbon at 3, and we have an sp hybridized carbon at 4. All right, so then we've got some substitution, we've got some dimethyl groups, and so what we'd end up with, and importantly, notice that the substitution, and when we number, we can number left to right or right to left. The only rule that I guess we want to talk about is that it's going to be always give alkyne lowest number. And so in this case, what we're going to end up with, the name is going to be 7,7-dimethyl. How are we going to locate the alkyne, do you think? Yeah, we're just going to call it 3. We don't have to call it 3,4. We just call it 3. It's assumed that it's continuing down the chain. And so we'll say 3-octyne. All right, so let's also say that. Always give alkyne lowest number. And so we also give the -ine suffix
That was my
there.
question.
Yeah, so it's just instead of -ane or -ine, we're now doing -ine. And that's pretty easy to remember, I think, given alkane, alkene, alkyne, just whatever it is. All right, so a reminder of what a triple bond really looks like in space. So we've got these sigma bonds, but we've also got some pi bonds involved. And so we're going to have pi bonds straight up and down in the plane of the paper as such. But then we also have to have another pair of p orbitals involved. And so geometrically, where are they going to be?
Kind of diagonal.
Yeah, they're in and out of the board, right? And so that allows us to use our 3 directions. We've used the x direction in our sigma bonds. We've used the y direction with our red p orbitals. And now we're going to use the z direction for the other p orbitals. And so that's in and out of the paper. So those look kind of like that. All right, so we get that pinwheel looking thing whenever we have an alkyne. All right, so another important thing, and this is going to be the big, honestly, the biggest deal about alkynes is their acidity. And so we're going to go ahead and also give a section to acidity. And so what we'll say is that as an sp hybridized carbon, it's going to have 50% S character. And so what that does is that, let's see, so that makes a carbanion relatively stable. Okay, so anytime we have a terminal alkyne, for example, we could use just a generic terminal alkyne. And so we'll react it with a pretty strong base, and very commonly you'll see something like NH2 as the base in question. So that, of course, would be in equilibrium, and so if our alkyne is acting as an acid, it's going to donate its proton to the NH2, so over here we end up with RCC, where we've deprotonated. So, and this is a little eye-looking. We're not used to seeing a negative charge on a carbon, but it's treated like any other negative charge. And then over here, of course, we've got our sodium, I guess, which is counterbalancing that charge. And then we end up with NH3 having accepted that proton. So what's the pKa of ammonia NH3?
The strong base.
Yeah, so it's about 36, which makes NH2 a really, really, really strong base, right? That's way above 11 for sure. So it's a very strong base, and it turns out the pKa of a terminal alkyne is going to be around 25. And so the stronger acid is our alkyne here, and so that means that the KEQ of this reaction would be greater than or less than 1. Well, what's going to be favored, reactants or products? Definitely products, right? Our stronger acid punches through to the other side, and so we end up with a KEQ greater than 1. We'll also say that our KEQ favors products. All right, so I'm making a big deal about this acidity. And so the reason I'm making such a big deal about this acidity is the fact that, well, whenever we've been using nucleophiles in the past, we've for the most part been using oxygen nucleophiles or nitrogen nucleophiles. But one of the big challenges of organic chemistry is making new carbon-carbon bonds, right? We're always trying to make these big complex carbon skeletons. And so we don't always want to just add some sort of oxygen in. We want to add actual new carbon-carbon bonds. And so this is a strategy to do that. So for example, what we can do is we can take something that looks like this. We can react it with our strong base here, so our sodium NH2. And so what we'll get is this deprotonated alkyne. So once we've got this deprotonated alkyne, what we're going to do is we're going to throw it in with a primary alkyl halide, such as this right here. So we can see clearly that's primary. And so we're just going to do an SN2 reaction. So we're going to start at our nucleophile, which is our negative charge on the carbon. And so we're going to draw right into our alpha carbon as such. And so what we end up with, let's see, is this product right here. And let's count and prove that that's what we get. So we've got 1, 2, 3, 4, 5, 6, 7. And so here we've got 1, 2, 3, 4, 5, 6, 7. So what we've been able to do is right here we formed a new carbon-carbon bond. And so I just want to say congratulations. This is like your first step to actually being an organic chemist. This is the goal all along. This is what most people are working on, you know, when they're doing research. They're trying to form new carbon-carbon bonds. And so this is the first time that we've seen really a synthetically useful way to do that in this class. Okay, it's 10:44. Let's talk exams. All right. So I thought the average might be a little low. The average on this one, I don't remember exactly. The average was around a 118. The mean was also around a 118. Oh, yeah, sorry. So if it makes you feel any better, Meldrum said that he once gave an exam that was like a 55 average. average. So that guy, yeah, we didn't do that. I also heard that there was a bio exam with like a 48 average a few years back, so we're not the worst in the world. All right, so my very, 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 very rough grade breakdown for this exam. Very, very, very rough. The AB line, we're gonna put around a 140, which is a 70%. Good God. The BC line, we're gonna put around a 115. The CD line is around a 90. And the other one is around a 65. All right, so this gives us a pretty good distribution, pretty comparable to what we've seen in the other exams. And so I love you guys so much that I've gone one step further. You're not going to just be getting back your exam grade. What I've done is I've also gone ahead and figured out what your probable score is for the class, and I mean grade, letter grade is for the class going into the final, assuming that you've done average on the homeworks. All right, so if you've aced these homeworks, it might be slightly higher. If you've skipped 7 of them, it's probably going to be lower. So what I've done is on your exams, so you're going to get these back. So like I said, you're going to have a score, and so that's kind of where that breaks down to. But you're also going to have a letter grade at the bottom of your last page. So that letter grade is my best projection for probably about where you sit going into the final. I thought that that might ease some fears if we went ahead and did that. So, or
push you to work hard. I'm not gonna look at it. A through G.
So this is H through O. And this is everything from C onward. Yep.
So today we're talking, is it 4?
Yeah.
Do you have, are you having office hours tomorrow?
I'm hoping to. I just got to get my schedule figured out. I'll have something out this afternoon.
Okay.
I don't know. I'm just saying. I'm not actually there. That'll speed up some things.
And also, how do you calculate when you're weighting these? Like, if we got like a certain letter on every exam, but obviously that number relates to a different distribution, how do you use that when combining them?
I total everything up and then find a good distribution.
Okay.
I just total. Fine. I'll be really good.
Well,
And also, I have numbers on kind of what the grade distribution looks like right now. So there's about 25% A's, 35% B's, 28% C's, 11% D's, 2% F's. And that doesn't add up to 100 because rounding errors. Yep. I'm just gonna. Okay. Why is it a weak base? It's a weak base. It's acetic acid. And I think it's fine.
How's your ankle doing? I have no idea what's what.
It's okay. It's just, yeah, I think.
We can't do it. I didn't hear that.
Wait, you said it. I didn't see it.
Oh, because you're.
Yeah, so basically we have cases where we have good and great miles to good bases, and so we have to determine which one. The secondary is how we determine that. So we have a strong base, we're going to go with the base system. The base system means if that concrete is below 11, then it's going to be good. Yeah, and it's ultimately going to be about the stabilities. Just hide that. So it has to do with the stability. Ultimately, with the basicity, yeah, it just depends on, because we've got ultimately four different pathways, right? So whatever is going to occur is because of the rate determining stability.
Okay. So it's not so much the why the mechanisms, but just like.
Yeah, and so I'm all.
I know there's 75. What the fuck? Look. I got 106. Oh, wait. This is the exact grade I got before. Look, you see, it's a 25-point jump. So after looking, the CB line's 75. So that's 102. So I got like right below like, what the hell?
Yes,
What the hell?
Yeah, just email me with that so I can get it down into my spreadsheet. I don't care when it is. It's perfectly fine. Yep. There you go. Oh, I'll just let you do that part. I trust you to do that. All right.
I just want to say, Dr. Walker, I don't know how I did it, but all three exams I got like the same grade roughly.
Yeah.
I don't know how.
Well, that means you probably improved some on the last one. Then.
Depends. Cause I keep being like right above the 75 range. I'm just like,
Yeah.
so I need to do well in the final, I guess.
Yeah.
So I'll see you next week. Have a good one.
Friday, right?
He said I'm not coming Friday. So I had a question.